Hello, good morning. Today I'm going to walk you through a smart vision project. What you're looking at on the slide is the system I'm going to walk you through today. On the left, a raw 1280 by 720 webcam feed of an indoor hallway, and on the right, the same scene interpreted by our pipeline at 30 frames per second. The floor is segmented in blue. Dynamic obstacles are bounded in yellow with confidence scores, and a navigation command move forward synthesized from the fused walkability map. This is Smart Vision. Real-time indoor navigation from a single RGB camera running locally with no specialized sensors. I'm not here to show you a model. I'm here to show you a system. Everything interesting about this project lives in the system's engineering. The networks themselves are off the shelf. What we built is the machine that makes them usable in a closed-loop control problem where a human being is the actuator. There are 3 takeaways. Why assistive AI is fundamentally different from benchmark AI, why we threw away 2 hardware architectures before we found the right one, and how the final reference architecture actually works.
So, on the next slide, we can see that accuracy is not always equal to usability. Assistive AI is a closed loop control system, not a static benchmark. That distinction is the whole game. When you evaluate a vision model in research, you compute mean IOU on a held out test set and publish. The evaluation is decoupled from time. Nothing happens between these predictions. That breaks the moment a human enters the loop. The model's output is consumed by someone moving through the space at roughly 1.4 meters per second. And 2 failure modes appear, but have no analog in benchmark evaluation. First, we have high accuracy plus high latency equals unusable. If the model is perfectly correct about where the obstacle was 300 milliseconds ago, the user has already taken a step. Stale data causes collisions. Secondly, high accuracy plus unstable output equals unusable. If the model is correct on each individual frame, but the decision oscillate left, right, forward, go backwards, the user receives contradictory information and becomes disconnected. The system can be right 100% of the time and still be useless. The chat on the right shows what this looks like. System usability stays at 1 meter across the low latency band, then falls off the cliff across around 150 milliseconds. No graceful degradation past the threshold. The system is no longer providing assistance, it is providing risk. In navigation, latency directly translates into high risk. That is the constraint that drove every architectural decision I'm about to describe.
So I'm going to walk a little bit through the gap in indoor navigation. Quickly, let's discuss what we're competing against. The white gain gives tactile distance, but no semantics and free space understanding. GPS is essentially useless indoors. A single beam LiDAR gives distance to a single point, no semantics and no spatial coverage. Vision, done correctly, is the only modality that delivers all 3. Distance estimation through scenery or through scene geometry, semantic understanding of every pixel, and dense free space estimation across the entire view of the field. That last column is what makes navigation possible. You cannot route a user around an obstacle if you only know about 1 pixel of space. Dense semantic plus spatial understanding. That is the requirement.
So, next up, the hardware graveyard. The early phases. Phase 1 was 2 architecture failed because we got to the correct one. I want to summarize them because every design decision in a final system is a direct response to something that broke here. Phase 1 was LiDAR plus YOLO sensor fusion. TF Mini Plus single beam LiDAR BNO85 IMU webcam stream for YOLO. This entire structure failed because the camera tells us what, LiDAR tells us how far it is. IMU compensates for the user's position. It failed because a single beam LiDAR returns one range measurement per sample. You cannot build an obstacle map from one ray. The IMU drifted faster than we could integrate. So the beam ended up sampling the ceiling, the floor, or any arbitrary points mid-rate. And even when we got clean readings, we hit semantic blindness. A half open door, a person, and a code track all produce indistinguishable returns. The depth signal had units but no meaning. The sparse depth ambiguity, single beam cannot estimate 2D free space geometry. Phase 2 was Hessian glasses. We pivoted to an integrated variable marketing promise of an open developer ecosystem and low latency video stream. The reality was something very different. It was a closed firmware ecosystem with a broken or unimplemented video API. We spent 2 weeks trying to break into the device, RTSP, network interception, custom firmware, and the most we ever achieved was a multi-second compressed stream for a system with a 150 millisecond safety threshold. That's not a slow pipeline, it's a non-functional one. The lesson encoded into everything that follows. We'll never build on a platform where we don't own the interface loop end to end.
Next, I'm going to talk through phase 3, the reference architecture. This is the architecture that we are releasing. So what we are using is Apple Silicon M series, PyTorch with the MPS backend. The deployment goal at this stage was deliberate. Maximize development velocity to prove the algorithmic core. Embedded hardware comes later. The data flow is raw camera frames fan out to 2 parallel branches. So branch 1 is the seg worker. It runs asynchronously. It's a dense walkable floor estimation, the slow, expensive pixel level understanding of the scene. It produces a segmentation mask. Branch 2, which is YOLO V8 Nano, this runs synchronously on every frame. So a sparse dynamic obstacle detection. It produces confidence scored bounding boxes. Both outputs flow into the mask fusion engine, which performs confidence fusion and temporal smoothing to produce a unified walkability map. The map feeds the navigation advisor, a spatial logic state machine whose decisions were emitted to a non-blocking audio and visual output layer. So essentially, there are 5 stages, 2 parallel inference branches. Each box on this diagram exists because of something that broke in the previous 2 phases that Utkarsh described, or because of an engineering challenge that I'm about to describe.
So let me talk about branch 1, which was finding the floor with a segformer. The segformer worker performs tense pixel level prediction mapped to walkable classes: floor, carpet, rug, stairway. This branch was where we hit the central trade-off of the entire project: detail versus frequency. On the left, we can see segformer B4 model, the heavyweight variant. Sharp boundaries, architecturally correct mask. Look at the table legs and the carpet edge, crisp and sharp. But these had a low FPS, 330 milliseconds of latency, more than double the 150 millisecond threshold. The model is right about the world, but by the time it's right, the world has moved. Unusable for real-time control. On the right, we have segformer B0 variant, the lightweight variant. Boundaries are noticeably rougher. And then there's the pixelation across the carpet edge, which we can see very clearly. The geometry is approximate, but 10 FPS, 100 milliseconds inside the threshold. This is something which is usable. We chose B0 model, not because it's the better model. It isn't, but because it's the better component in the system. This is the kind of decision academic boundary benchmarks which it cannot capture, and the system engineering forces you to confront.
I'm going to talk a little bit more about the dynamic obstacle override. So YOLO version 8 Nano, which is the Nano variant, is pre-trained on a dataset called COCO. which is a 320 pixel input, 30 to 60 millisecond inference. The question is, if we already have semantic segmentation, why do we need object detection? There's a 3-panel answer. So step 1 is visual ambiguity. A backpack on the carpet with similar texture and color to a pixel level classifier. The backpack looks statistically similar to the carpet pixels. Step 2, segmentation hallucination. SegFormer extends the walkable mask through the backpack. The blue region covers the ground that is not actually walkable. This is not a bug. It's a failure mode inherent to semantic segmentation, when objects share visual statistics with the background. If the system ships with only branch 1, the user walks into the backpack. And the last step, step 3, YOLO hard override. YOLO is an instant detector. It reasons about object shape and structure, but not pixel statistics. So it produces a bounding box around the backpack regardless of texture similarity. Any pixel inside a YOLO box is forced to be an obstacle state, overriding SegFormer. This is sensor fusion between both models instead of two physical sensors. Each model has a failure mode, and the combination has neither.
Let me talk more about the Fusion engine. The Fusion engine is intentionally simple because simple logic is a debuggable logic. Walkable equals floor and not obstacle. Layer 1 is the SegFormer floor mask. Layer 2 is the YOLO obstacle mask. The result is the fused safe path. The floor mask with obstacle footprints subtracted. The Boolean operation is per pixel and trivially parallelizable. The interesting engineering isn't in the logic. It's in making sure the two input masks are temporally and spatially aligned at the moment of fusion, which is where the asynchronous branch design earns its keep.
I'm going to talk a bit about the spatial reasoning and decision matrix. The fused map is dense, and the user needs a command, straight, left, right. Converting one to the other is the navigation advisor. The policy is conservative by design. We ignore the top 45% of the frame, which is usually ceiling, distant walls, and far-field clutter that has no bearing distance or no bearable things on the next step. The remaining region splits into 3 vertical columns. For each, we compute the obstacle ratio, the fraction of non-walkable pixels. Center first. If the center is clear, we always say forward. Always. And this is a strong bias, and it's deliberate. If the center is blocked, we compare left and right against the safety threshold, but not against each other. We need to know a side route is safe, not merely safer. We would prefer to move forward unless side margins are strictly safer. Lateral redirects require positive evidence of a safe alternative. The forward bias is psychological as much as it is algorithmic. The constant lateral commands feel jittery and erode user trust. Forward commitment feels natural. The policy is tuned for the experience of being guided, not just the geometry of being rooted.
Let me talk about the temporal stabilization which we are doing and how we prevent command oscillation. At 30 fps, sensor noise and small camera jitter cause column scores to fluctuate frame to frame. A pure per frame policy emits forward, forward, left, forward, right, useless to the user. 3 mechanisms fix this. A history buffer holding the last 8 frames. The committed output is the majority vote. A single noisy frame cannot flip the command. Hysteresis, a mathematical bias toward the current state. So, the proposed new state has to beat the current state score by a margin, not merely tie it. And then there's the asymmetric thresholds. Stop requires stricter consensus than move, because we rather miss a stop by a frame than emit a false stop that breaks the user's stride for no reason. The diagram shows the effect. Raw per frame output is jarring. After the 8 frame majority plus hysteresis filter, The output is clean and committed.
There were three engineering challenges that made this architecture really run. I'm going to discuss a little bit about the first, which was the 15 frame per second bottleneck. SegFormer B0 takes 150 milliseconds as we described earlier. In a naive synchronous pipeline, that single call caps the entire system at 6 frames per second. So, what we did, the solution, a decoupled async worker with the latest frame wins policy. So, thread 1, the main loop, runs the camera capture, YOLO, and the navigation decision continuously. Thread 2, the seg worker runs SegFormer on its own clock and writes results to a shared buffer. If thread 2 finishes 2 inferences before thread 1 reads, the older result is dropped. We never queue stale segmentation. The freshest mask wins. This moves the main loop from 6 frames per second to roughly 18 frames per second. The segmentation map is allowed to be 100 to 150 milliseconds stale because the walkable layout of a room changes slowly. The dynamic obstacle channel, YOLO, is the one that has to be fresh. And it is.
Now let me talk about the second challenge, which is GPU contention and MPS crashes. So there was this assumption that we can run YOLO and SegFormer in parallel on the M series GPU. In reality, PyTorch's MPS backend is not thread safe. Concurrent inference calls don't yield parallelism. They yield fatal crashes, not slowdowns. Hard crash that take down the entire process. We diagnosed this the hard way over several days. And there was a very simple fix, a global mutex, MPS locks, that serializes all GPU operations across threads. YOLO and SegFormer takes turn. They never touch the GPU simultaneously. This trades theoretical throughput for hard system stability. You give up the parallelism you came for, but you get a process that doesn't crash mid-walk. For an assistive system, that trade-off is non-negotiable. This is also the single biggest argument for migrating to CUDA, which I'll get to in a bit.
So, the third challenge was non-blocking audio. The challenge nobody anticipates until it really happens to them. The issue, PyTTSX3, the TTS library that we used initially, blocks the main thread while speaking. A command line like turn left takes 500 milliseconds to synthesize and play. If TTS runs on the main thread, the perception loop pauses for a half second every time the system speaks. The user is walking blind at that time when the system is actively warning them. So the solution was a daemon audio thread with preemptible command queue. The main thread enqueues and immediately returns. The audio daemon DQ speaks and enforces a 2.5 second cooldown to prevent overspeaking when conditions change rapidly. Duplicate rejection is built in. Repeated commands within the cooldown window are silently dropped, and the perception loop never blocks an audio. The user never walks blind, and guidance feels measured rather than frantic. So now that you've seen every component, here's what it looks like running end to end on our system.
Path on your right. Go ahead. Path on your left. Go ahead. Path on your left. Go ahead. Path on your right.
That is what the system as it ships today looks like. Let's talk about what works, what doesn't, and where it goes next.
This is timely and non-disruptive. The ugly, monocular depth blindness. A single RGB camera fundamentally cannot sense a descending staircase. The visual cue requires depth perception, which we don't have. This is the hard architectural limit, not something a better model can fix. It is the highest priority item for the next phase. And there are two optimizations that backfired, which is worth flagging because other teams will hit them. First, we had the naive frame resizing below 320 pixels. It meant faster inference, but YOLO bounding boxes computed in the resized frame no longer aligned with the segmentation mask at a different resolution. The fusion engine misaligned obstacles relative to the floor. This meant we should never resize asymmetrically across the pipeline stages. The second was the temporal mask blending, meant to reduce flicker. Actual result? Ghost walls. When a person walks across the frame, the blended mask retains a faint silhouette of where they used to be. Classified as obstacle, the user gets warned about walls that don't exist. We remove temporal blending entirely. The decision level smoothing on slide 10 handles stability without ghosts in the spatial layer.
So the path forward, you may be wondering what that would be. There are three primary changes that we would like to make. The first one is the hardware shift. We want to be off the MacBook and into an NVIDIA Jetson or a Nano. The biggest reason is CUDA. Real parallel GPU execution, YOLO and SegFormer can finally run concurrently on separate streams instead of contending through a mutex. The second is model optimization. INT8 quantization through TensorRT. On the NVIDIA hardware, we can expect further 2 to 4 times reduction in per frame latency. That headroom is what lets us add a third asynchronous worker for depth estimation. And finally, sensor upgrade. Stereo depth via Intel RealSense. Direct solution to the descending staircase problem. Not inferred from a single beam like the failed phase 1 LiDAR. Not absent like the current pure RGB pipeline. Dense and metric across the full field of view. A stereo camera provides a depth map in every frame which fuses cleanly into the existing engine as a third input layer. Form factor moves from laptop to a wearable vest on the chest, RealSense at the sternum aimed forward. That is where the product lives. Our final takeaway is a real-time edge AI requires treating the neural network not as a magic oracle, but as one gear in a complex synchronized machine. The model is one component. The latency budget is a thread topology, the GPU concurrency model, the audio daemon, the temporal filter, the decision policy. All of that is the actual product. Thank you so much for listening to us talk about the Smart Vision glasses in our project. My name is Anvi Mehta.
And I am Utkarsh Narayan, and this was a product demo.